Hi everyone, today we are going to dive deep into the foundations of machine learning, linear regression, cost functions, and gradient descent. Imagine you are a real estate agent trying to predict house prices based on square footage. On the screen, you see our data. A 1,000 square feet house costs $250,000 and a 2,000 square feet house costs $500,000. But what happens when a client asks for the price of 3,000 square feet house or maybe 1,500 square feet? This is where linear regression comes in. Linear regression is a supervised learning model, which means it needs labeled data to train on. In simple words, we already know the answers while training. With linear regression, our goal is to draw a straight line that fits most, if not all, of these data points. If you see the graph on the screen, you will see multiple red dots. Each red dot represents one house. Obviously, to keep things easy, we have just taken two data points. Mathematically, we describe this line as y equal to w times x plus b, where x is our input, square footage, w is the weight or slope. It tells us how much the price increases for every extra square foot. B is the bias or y-intercept. It shifts the line up or down and represents the base price. Together, W and B are our parameters. And our main goal in this video is to find the magic values of W and B that gives us the most accurate predictions. For example, you can take both W and B as 100 and predict the prices. Whether they are accurate or not, it's another matter. Now the big question is, how do we know if a line is actually good? If I randomly choose the values for W and B, the line might be completely off, nowhere near our data points. So we need a way to measure how wrong our model is. That's where the cost function comes in. To be precise, a squared error cost function, usually represented by J, think of the cost function as a penalty score. At every data point, we take the predicted value represented by y hat, subtract the actual value y, square the difference so the error is always positive, add everything up and take the average. The formula looks like this. You might notice a half in front of the equation. That's just a mathematical trick. It makes the calculation easier later. And our ultimate goal is very simple. Minimize J. The smaller the cost, the better our model is performing. Now, we could keep guessing random values for W and B, but that would take forever to get optimal values. Instead, we use an algorithm called gradient descent. Imagine you are standing on a foggy mountain. You want to reach the bottom, but the fog is so thick that you can't see the valley. So, what do? You feel the slope under your feet and take a small step in the direction where the ground goes down the steepest. Then you stop, feel again and take another step. You follow the same until you reach the bottom of the hill. And that's exactly how the gradient descent works. In math, we update W and B like this. After working through the derivatives for the squared error cost function, we get the final update rules. As you can see in the equation, we have alpha, also known as learning rate. If alpha is too big, you take giant jump and might overshoot the minimum. If alpha is too small, you take tiny baby steps and training becomes very slow. Eventually, you reach a point where the ground feels flat. This is called convergence. At this point, W and B stop changing because we have reached the minimum cost. Let's quickly summarize everything. We use linear regression to predict the values based on trend. It is mathematically defined as y equal to w times x plus b, where x is input, w and b are parameters, and y hat is the predicted output. The cost function tells us how well our model is performing, and our goal is to minimize it. Gradient descent helps us find the optimal values of w and b. It uses alpha, the learning rate, those baby steps we talked about, and updates both parameters simultaneously. Now, enough of the theory. It's time to practice what we have learned. We are not using any fancy libraries like scikit-learn today. just pure Python and NumPy. So let's just start by importing the NumPy library. Then let's define our data sets, which is extra. Then one data. Let's print for the logging purpose. Extra. So let's begin by defining the cost function. I'm naming it as compute cost, and it will need parameters x, y, w, and p. Now we need m, which is x.shape. We need the number of elements from the x, so let's define another variable, cost sum, which is initialized as 0. We will run a loop for these values. So what we will be doing, we will be predicting with the past arguments. Then if you remember, we need to calculate the square error, right? Thus we will update the cost sum plus the predicted value minus the actual value, and we will be squaring it. Then when the loop gets finished, we get the sum. We need to divide it by 2m, if you remember from the formula. Yes, and I'll put a bracket here as well. That's it, and return this final cost. So we have defined the compute cost function. Now we'll be implementing the gradient descent functions. So the first part is to compute the gradient, the derivative part. So let's define compute gradient. And we will be needing the same arguments x, y, w, and p. Now we will be needing the m again here, and first parameter, yes. So let's define the initial values of dw and db and take them as 0. We will be updating them. Yep. Now we will be running a loop for this, for I in range m. Now we'll be predicting the value again. I'll write it quickly. So this is a prediction. Now if you remember from the formula, we need to update the w and b from the derived formula. So we'll be adding all as we need summation. Let's update the w first. That's equal to, what was that, prediction minus actual, and we need to multiply it with the value of x. So dw is updated. Similar with the p, it's simply just predict minus y of I. Leave the spaces for formatting purpose here. Yeah. So this has been added, and finally return this value and divide by m, if you remember. So this calculates the gradient for our formula. These are the derivative part, and we'll be defining the whole function, which will be using this compute gradient method. So let's define gradient descent. It will be needing x, it will need y, it will need an initial value of w, it will need an initial value of p. We need to start somewhere, right? We need an alpha, the learning rate, and we need the number of iterations. Why we are taking iterations, I'll explain in a while. So for better understanding purpose, I am reassigning those values as w and b. Yep. So let's start a loop for r in So why we are using iteration? We need to follow the gradient descent until we reach the convergence. So we need a number to run the loop until we reach the convergence. It can be any number. So we are defining them as iterations. So derivative w and b from the compute gradient method. Compute gradient will be passing x, y, w, and b. And whenever we're getting this value, we need to update w such that w equal to w minus alpha times this derivative term. Similarly with b, yeah. So this is updated, and for logging purpose, and we can understand this better, let's log everything. So if I 100 equal to 0, then let's print something, iteration number, so we can see everything working and get cost at that point. Let's call it compute cost function here. Let's pass x, y, w, and p here as well. So this will be logging the cost here. Now let's finally return the value of w and b. So we are pretty much done with defining all the functions. Let's initialize everything and run it. So we need an initial value of w, right? You can take 0, you can take 100, you can take any value. I'm taking 100 for example. Same with b, you can take any value. Let's take 0 for example. We need to define number of iterations. It depends, but let's say we need to start with 1500 iterations. And we need an alpha, a learning rate. Remember, do not take it too small or too large, but it's always a good idea to test and try and test it out. So let's take 0.1. So we are done defining almost all the parameters. Now let's train the model with the help of the functions we have defined. So we will be getting w final and b final from the method. Let's pass the x train, y train, w init, then b init, then alpha, and iterations. Yeah. So this will be returning w final and b final. Let's log this value so we can see it. W final. Same with b. So this is pretty much done. Now before we predict the price for 3000 square feet house, Let's test it with the values we already have. So let's print for 1000 square feet first. So W final will be used. Remember, we have scaled down. We are not using actually 1000. We'll be using 1 instead to keep calculations faster and concise. B final. Same way, I'll just copy it, and same with 2000, and we'll be needing for 3000 as well, right, for prediction. So I'll just change the values quickly. Here 2. I think decimal would be better. Here 3. Yeah, pretty much it. And this is our prediction we want to make. So we are pretty much done with the code. So if you see, we have imported the numpy, we have defined the parameters, and we defined the cost function, which will be calculating the cost. Then we have the gradient method, which will be calculating the derivative part of the equation, and the overall gradient descent method, which will be using compute gradient method to actually update the W and B and return the final value. Then we have taken initial values. We have trained the model. Basically, we got the final values for W final and B final. We logged it and we actually tested it. Sorry, I just noted the thing. We have to return W and B after the loop completes. So keep that in mind. Here too, yes, everything's look good. Let's run it. So if you see the output carefully, this is our training data set and there are multiple iterations. So let's see, the cost at first initially was 12,000 something. If you see, it went down, it became 0 and it started to rise again. By the iteration 1400, it became 2 from 0, 9 to 5. So I think we have taken a lot more iteration than required. So let's change the iteration to 900. That seems a good number. And yeah, let's run it again. So if you see, the cost is minimized. If you see, it started from 12,000 and became almost 0.001. Then it gave the final value of W to be 249.9 and B to be 0.09. Then it predicted the price. If you see, those are pretty accurate one. So if you see, 250,000 for the 1000 square feet one and 499.97, almost 500,000 for the 2000 square feet one. And it predicted 749.92 for 3000 square feet house, which is not a bad prediction, right? So let's see what happens when we tweak the values here. So for example, let's change the learning rate. So we have taken alpha 0.1. What happens if we double it? What do you expect? Let's see. If you see, the cost was minimized at the way earlier, like if you see, like around 200 it was minimized and it started to rise again. So this learning rate was not ideal for this number of iteration. Either we have to reduce the iteration or we have to like change something else. What happens if we take 0.5? It's like 5 times of the initial one. The minimum cost reached in the second at the 100th iteration itself. So what happens if we take a very small alpha, 0.01? See, the cost was although minimizing, but it never reached 0, which was the case with the 0.1. So let's change it back to 0.1 and run this again and see. This is our prediction. And that's it. You just built a machine learning model from scratch. You have defined the math, measured the error, and literally walked down the mountain to find the best solution. Thanks for watching. I'll see you in the next one.